We were occupied the last time we met in considering the general character and arrangement as regards the fluid portion of a candle and the way in which that fluid got into the place of combustion. And now I have to ask your attention to the means by which we are enabled to ascertain what happens in any particular part of the flame, why it happens, what it does in happening, and where, after all, the whole candle goes to. Because, as you know very well, a candle being brought before us and burned disappears, if burned properly, without the least trace of dirt in the candlestick. And this is a very curious phenomenon. We will examine this dark part first. And now I take this bent glass tube and introduce one end into the middle of the flame. You see at once that something is coming from the flame. At the other end, you will see that something from the middle part of the flame is gradually drawn out and goes through the tube and into that flask, and there behaves very differently from what it does in the open air. It not only escapes from the end of the tube, but falls down to the bottom of the flask like a heavy substance, as indeed it is. We find that it is the wax of the candle made into a vaporous fluid, not a gas. You must learn the difference between a gas and a vapor. A gas remains permanent, a vapor is something that will condense. If you blow out a candle, you perceive a very nasty smell, resulting from the condensation of this vapor. This is very different from what you have outside the flame. And in order to make that more clear to you, I'm about to produce and set fire to a larger proportion of this vapor. For what we have in the small way in a candle, to understand thoroughly, we must as scientists produce in a larger way if needful, that we may examine the different parts. Here is some wax in a glass flask, and I've made it hot as the inside of that candle flame is hot and the matter about the wick is hot. You see that the wax has become fluid, and there's a little smoke coming from it and vapor rising up that I can set on fire. This then is exactly the same kind of vapor as we have in the middle of the candle. I have arranged another tube carefully in the flame, and I was able, by a little care, to get that vapor to pass through the tube to the other extremity, where I will light it and obtain absolutely the flame of the candle at a place distant from it. Now, look at that. Is not that a very pretty experiment? And you see from this that there are clearly two different kinds of action. One, the production of the vapor, and the other, the combustion of it, both of which take place in particular parts of the candle. I shall get no vapor from that part which is already burnt. If I raise the tube to the upper part of the flame, so soon as the vapor has been swept away, what comes away will be no longer combustible. It is already burned. How burned? By burned thus. In the middle of the flame where the wick is, there is this combustible vapor. On the outside of the flame is the air which we shall find necessary for the burning of the candle. Between the two, intense chemical action takes place, whereby the air and the fuel act upon each other, and at the very same time that we obtain light, the vapor itself is consumed. If you examine where the heat of a candle is, you'll find it very curiously arranged. Suppose I take this candle and hold a piece of paper close upon the flame. Where is the heat of that flame? Do you not see that it is not in the inside? It is in a ring exactly in the place where I told you the chemical action was, and even in my irregular mode of making this experiment, if there is not too much disturbance, there will always be a ring because the heat is where the air and the fuel come together. This is most important for us as we proceed with our subject. Air is absolutely necessary for combustion, and what is more, I must have you understand that fresh air is necessary, or else we should be imperfect in our reasoning and our experiments. Here is a jar of air. I place it over a candle, and it burns very nicely in it at first, showing that what I have said about it is true, but there will soon be a change. See how the flame is drawing upwards, presently fading, and at last going out. And going out why? The jar is full of air, partly changed, partly not changed, but it does not contain sufficient of the fresh air which is necessary for the combustion of a candle. These are all points which we, as young chemists, have to gather up. And if we look a little more closely into this kind of action, we shall soon find certain steps of reasoning extremely interesting. We have the case of the combustion of a candle, we have the case of a candle being put up by the want of air, and we now have the case of imperfect combustion. And this is to us so interesting that I want you to understand it as thoroughly as you do the case of a candle burning in its best possible manner. I will now make a great flame because we need the largest possible illustration. Here is a larger wick made from these cotton balls. All these things are the same as candles after all. If we have larger wicks, we must have a larger supply of air, or we shall have less perfect combustion. Now, look at the black substance going up into the atmosphere. There's a regular stream of it. Look at the soot that flies off from the flame. See what an imperfect combustion it is, because it cannot get enough air. What then is happening? Why, certain things which are necessary to the combustion of a candle are absent, and very bad results are accordingly produced. But we see what happens to a candle when it is burnt in a pure and proper state of air. Recall the charred ring on the paper. And on the other side, you see the burning of a candle produces the same kind of soot, charcoal, or carbon. Let me explain to you, as it is quite necessary for our purpose, that although I take a candle and give you as the general result its combustion in the form of a flame, we must see whether combustion is always in this condition or whether there are other conditions of flame. And we shall soon discover that there are, and that they are most important to us. Here is a little gunpowder. You know that gunpowder burns with flame. We may fairly call it flame. It contains carbon and other materials which altogether cause it to burn with a flame. And here is some pulverized iron or iron filings. Now, I propose burning these two things together, my object being to make the gunpowder set fire to the filings and burn them in the air, and thereby show the difference between substances burning with flame and not with flame. Now, here is the mixture, and when I set fire to it, you must watch the combustion, and you will see that it is of two kinds. You will see the gunpowder burning with a flame and the filings thrown up. You will see them burning too, but without the production of flame. They will each burn separately. There is the gunpowder, which burns with a flame, and there are the filings. They burn with a different kind of combustion. You see then these two great distinctions, and upon these differences depend all the utility and all the beauty of flame which we use for the purpose of giving off light. When we use oil or gas or candle for the purpose of illumination, their fitness all depends on these different kinds of combustion. There are such curious conditions of flame that it requires some cleverness and nicety of discrimination to distinguish the kinds of combustion one from another. For instance, here is a powder which is very combustible, consisting, as you see, of separate little particles. It is called lycopodium, and each of these particles can produce a vapor and produce its own flame. But to see them burning, you would imagine it was all one flame. I will now set fire to a quantity, and you will see the effect. We saw a cloud of flame, apparently in one body, but that rushing noise was proof that the combustion was not a continuous or a regular one. This is not an example of combustion like that of the filings I had been speaking of, to which we must now return. Suppose I take a candle and examine that part of it which appears brightest to our eyes. Why? There I get those black particles, which already you have seen many times evolve from the flame, and which I am now about to evolve in a different way. I have arranged the glass tube so as just to dip into this luminous part, as in our first experiment, only higher. You see the result. In place of having the same white vapor that we had before, we now have a black vapor. There it goes, as black as ink. It is certainly very different from the white vapor, and when we put a light to it, we shall find that it does not burn. Well, these particles, as I said before, are just the smoke of the candle. Why, it is the same carbon which exists in the candle. And how comes it out of the candle wax? It evidently existed in the wax, or else we should not have had it here. And now I want you to follow me in this explanation. You would hardly think that all those substances which flew around London in the form of soots and blacks are the very beauty and life of the flame, and which are burned as those iron filings were burned. I want you now to follow me in this point, that whenever a substance burns, as the iron filings burnt in the flame of gunpowder without assuming the vaporous state, whether it becomes liquid or remains solid, it becomes exceedingly luminous. What I have to say is applicable to all substances, whether they burned or whether they do not burn, that they are exceedingly bright if they retain their solid form, and that it is to this presence of solid particles in the candle flame that it owes its brilliancy. I have here a piece of carbon or charcoal which will burn and give us light exactly in the same manner as if it were burnt as part of a candle. The heat that is in the flame of a candle decomposes the vapor of the wax and sets free the carbon particles. They rise up heated and glowing as this now glows and then enter into the air. But the particles, when burnt, never pass off from a candle in the form of carbon. They go off into the air as a perfectly invisible substance. I shall tell you about this later. Is it not beautiful to think that such a process is going on, and that such a dirty thing as charcoal can become so incandescent? You see, it comes to this, that all bright flames contain these solid particles. All things that burn and produce solid particles, either during the time they are burning, as in the candle, or immediately after being burnt, as in the case of the gunpowder and iron filings, all these things give us this glorious and beautiful light. I've mixed potassium chlorate and sugar. I shall touch them with a drop of sulfuric acid for the purpose of giving you an illustration of chemical action, and they will instantly burn. Now, from the appearance of things, you can judge for yourselves whether they produce solid matter in burning. I've given you the train of reasoning which will enable you to say whether they do or do not. For what is this bright flame but the solid particles passing off? When the particles are not separated, you get no brightness. The flame of a candle owes its brightness to the separation during combustion of these particles of carbon. I can very quickly alter that arrangement. Here, for instance, is a bright yellow flame from propane in a Bunsen burner. Supposing I add so much air to the flame as to cause all to burn before those particles are set free, I shall not have this brightness. There is plenty of carbon in the gas, but because the atmosphere can get to it and mix with it before it burns, you see how pale and blue the flame is. The difference is solely due to the solid particles not being separated before the gas is burnt. You observe that there are certain products as the result of the combustion of a candle, and that of these products one portion may be considered as charcoal or soot. That charcoal, when afterwards burnt, produces some other product, and it concerns us very much now to ascertain what that other product is. This vessel captures all the products of the candle, and you will presently see the vessel's walls become quite opaque. The sides of the jar become cloudy, and the light begins to burn feebly. It is the products you see which make the light so dim, and this is the same thing which makes the sides of the vessel so opaque. If I take a spoon that's been in cold water, wipe it dry, and hold it over a candle so as not to soot it, you will find that it becomes dim just as the vessel's walls are dim. And now, just to carry your thoughts forward to the time we shall next meet, let me tell you that it is water which causes the dimness. I will show you that we can make it without difficulty assume the form of a liquid.